Okay, 14D is investing money by regular installments, which could be known as superannuation or an annuity. So it says at the top of the page here, an annuity is a fund where a certain amount of money is invested at regular intervals. So superannuation is the very common example that we use of this, where you're putting money into an account on a regular basis, saving it all up, it's collecting interest, and when you retire, you'll start to get your payments. Okay, so obviously this is going to involve series, and we need to be able to develop the series for each question because they will differ slightly, and the questions, they usually set them up to make sure that you have to be able to show that you can set it up and not just remember this is going to go to this formula kind of thing. Okay, so let me show you example number 1. Hurry up please, Finlay. An engineer pays $1,000 into a superannuation fund at the beginning of each year. Compound interest is paid at 9% per annum on the investment. What will be the value of the investment at the end of 35 years? Okay, it says compound interest. We're going to be using the compound interest formula, which is A equals P bracket 1 plus R to the power of N. Now the trouble is, it's not just one amount. They're putting in $1,000 every year. So the first amount of money that they put in, it's going to be in there for 35 years. Then the second amount, a year later, they put another amount of money in there, and it will be in there for 34 years, then 33 years, then 32 years, until all the way down, and you get into this last 35th year, and that last amount of money you put in there will only be in there for 1 year. And this is the series, okay? To show what is happening, we say A1, the little 1, stands for the first amount of money that has been invested. The first $1,000 in this case. So our numbers are, we have $1,000 being invested, 9% per annum, and the 35 years will come into it obviously as well. Using my compound interest formula, that first $1,000, just the first one, it will get compound interest of 1,000, 1 plus the 0.09 to the power of 35. Now what you will probably start to do very quickly, because I know I'll be doing it in the examples, is as soon as you have 1 plus your interest rate, put them straight together to be 1.09 to the power of 35, and it will save you time and working out on your paper. Okay? All right, moving on to the second amount of money. So a whole year passes, and this engineer puts another $1,000 in the bank. So this $1,000 is only going to be in there for 34 years because a year passed. And that pattern would continue. You could go A3, that would be 1,000, 1.09 to the power of 33. Now, I'm probably doing more than I need to. Usually 2 is probably enough to see what is happening. I've done 3. And then you can see the pattern. So I do an arrow coming down, and I say this is going to happen every year up to the 35th year. In the 35th year, they're going to put $1,000 in their account, and it will only be in the account for 1 year. So there'll be a power of 1 on that. Sometimes you have to be careful with the wording of the question. Sometimes they say the money might be invested right at the end of the year, so that last one might not get any interest at all. So they can be sneaky that way. Okay, so these A1, A2, A3, all the way down to A35, they are individual compound interest calculations on the 35 lots of $1,000 that these people have put into their account. I want to find the total amount, so I want to sum it up. Okay, so down here, I'm going to write total for the total amount that this person has earned. Now, the thing is, knowing this is going to be a series, if I go this way, my powers are getting smaller, which can be done, but it's not as nice. So what we tend to do is when we add them together, we start with the smaller one and we go up and make them bigger because the series is much nicer that way. So we start with the 1,000 times 1.09. You could add in a 1,000 1.09 squared because you know the next one's going to be in there. You can write as many in there as you want. I'm going to do it plus ... And then you go all the way down to the last one, which would be 1,000 1.09 to the power of 35. So I haven't even written the 33 and the 34, but I've used this to get myself kind of an expression here for what is happening with my series. If I want to sum that series, it's a geometric series. I use my geometric series formula, which has A that is equal to 1,000 times 1.09. That's my first term. R, as I'm going along here, each term in that series is getting multiplied by an extra 1.09. So that's R. N, how many terms do I have? Started at 1 and went all the way up through to 35, so I have 35 terms. So N is equal to 35. My sum formula, if R is bigger than 1, is A bracket R to the N minus 1 over R take 1. I am going to be summing 35 terms, so sum of 35. A is 1,000, R is 1.09 to the power of 35, minus 1 over 1.09 minus 1. And you put that into your calculator and you will get your answer. Yeah. Oh, yes, I missed a thing. Thank you. Yep, let's take that back. There should have been an extra 1.09 there. That's better. Sorry, A had that extra bit on it. Okay, so put in your calculator. What do we get? Big number, because they've invested $1,000 for 35 years, so that's at least $35,000 that they've put in, let alone all the interest that they've earned. Is that what you guys got? Yeah, so nearly $250,000. Okay, so that comes the lesson in financial planning of starting early and putting money in and investing it, and it can grow to something quite significant. But it just took 35 years to get there, but still. All right, that's the process. Let's do another one. Question 2. $10,000 this time is invested in a superannuation scheme on the 1st of July each year. Beginning in the year 2010, the money earns interest compounded at 8%. So we have, this is our amount of money, we have our interest rate over here, compounded annually. How much will the fund amount to by the 30th of June in 2030? Okay, so the first amount of money goes in on the 31st of July. How many years have passed to get to the 30th of June? That's the one day before the next amount of money would have gone in, right? So it's saying right before we make our very next instalment on the 1st of July, so the 30th of June in 2030, how many years is that? Sorry, how many years? 20 years. It is 20 years, yes. So there is 20 years there that we're going to be getting interest on. So the year 2030, they haven't actually put anything in the bank yet. Okay, so there's no term in 2030, if you like. but they're getting interest up to there. Does that make sense? Okay, so we're going to have 20 terms in our series. Our first one, they put $10,000 in the bank. It is earning 8% interest, which we can straight away write as 1.08. That's adding the 1 with our interest rate in our compound interest formula. That will be there for 20 years. The second amount of money goes in the bank, the $10,000. It's going to be there for 19 years. And the pattern continues down to the 20th year, which is, this is the deposit on the 1st of July in 2029. Does that make sense? 2029, they deposit it, but they would get a year's worth of interest going to the 30th of June the next year. All right? So that would be 10,000, 1.08 to the power of 1. Okay, so we've shown that we've got an understanding of how our terms are developing here, and I've been a little bit briefer than I was in the first one. Now I'm going to find the total of all of that, which means I'm going to add them together. Gentlemen, do you mind paying attention up here? Starting with the smallest one and working our way up into the bigger terms, we will have 10,000, 1.08. The next one would be 10,000, 1.08 squared. And then I'm going to go plus dot, 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 dot for all the other terms that I don't want to write down, and go to the last term, which was 10,000, 1.08 to the power of 20. Now we use our sum formula. So I'm not going to write the formula down again. I'm going to straight to sum of 20 and sub in my things. So the formula is A, which will be 10,000, 1.08. Then you open a bracket and it's R to the N. R is 1.08. There are 20 terms, so the power of 20. Minus 1 all over 1.08 minus 1. One of the other temptations that you might start doing straight away is just putting down here 0.08, subtracting the 1 straight off it. What did you get?
494,229.2.
Correct. Okay, so that was pretty much a repeat of the first question, but this one has extra parts to it. So let's move on to part B. How much will the fund amount be by the end of n years? It's asking me for a general equation of the sum. So if I use this line here, where I had, this was for 20 years, so I had a power of 20. I could generalize this to be the sum of n years. All that's going to change is that power of 20 is going to become an n, because that's the only spot in the formula where you sub n in. So it'll be 10,000, 1.08, 1.08 to the power of n minus 1 over 1.08 minus 1. Now, I can tidy that a little bit because I can't do anything with this bracket, but I could, that's all just numbers there. I could divide that by 0.08 just to get rid of the fraction. So if you type in 10,000 times 1.08 divided by 0.08, it's 135,000, good, 1.08 to the n minus 1. Just makes it a little bit of a nicer expression. Okay, there's still more parts. Well, let's see what else we can do. Question C. Show that 2031 is the year when the fund will first exceed $500,000 on the 30th of June. Okay, again, this kind of messes with your brain a little bit because the 30th of June actually means that our last deposit was in the year 2030. Okay? But that's okay. We want to show that it's going to cross over that $500,000 mark. Between n is, what would be the lower end? N equals what? That would be the higher end. 20. So when n equals 20, I'll sub it in and you'll see. If n equals 20, I would get my formula, which was 135,000, 1.08 to the 20 minus 1. We kind of already did this. This is the one that we did in part A. That one makes 494,229. That's what we got in part A. But if we now sub in when n is equal to 21, go that extra year, we will see it go over $500,000. So we sub it in 135,000, 1.08 to the power of 21, and it equals, that's right, and 55 cents. So that means, yeah, that 2031 is the first year that will exceed the $500,000. Okay? Part D. What annual installment would have produced $1 million by 2030? Okay, this means we're no longer depositing, what was it, $10,000? We're going to change that investment to try and make sure we end up with this final amount of $1 million that we're after. So let's start again with our series. I'm just going to squeeze it in up here at the top. I'm going to call it M for the amount of money, maybe M for money, that I need to invest. It would get times by my interest rate, which is still the 1.08. In 2030, we know that that is 20 years that we have to do this in. Okay? Then our A2 would be 1.08 to the 19, and we come all the way down to A20, we should be 1.08 to the power of 1. Okay? We take our sum by having M, put that lower one first, M bracket 1.08 plus M 1.08 squared plus all the way up to M lots of 1.08 to the power of 20. And we're going to sum it with our sum formula. The sum of those 20 terms will be the first term, which is M times 1.08. Then R to the N would be 1.08 to the power of 20 minus 1 over 1.08 minus 1. Okay, but now that I have this equation, I can say what I want this sum to be. And it said that we want to make sure that we clear $1 million in the 20 years. So we're going to put $1 million over here for the sum, and then we can solve the equation to find out what the M is. So I'm going to, what can I do with that? We could divide the 1.08 by 0.08 just to get rid of the fraction, which I think makes 13.5, is that right? Yeah? And then to get the M all by itself, you have your million over here, you're going to divide the 13.5 and that bracket underneath. So here's the million. We're going to divide the 13.5 and the 1.08 to the 20 minus 1. Divide that whole bracket, all that stuff underneath. Yeah. 20,231. Oh, 34, sorry. I wrote it, said the wrong thing. That's been rounded to the nearest dollar, so I think there's some decimal places after that. Okay, so yeah, if they can invest $20,000 every year, they'll have $1 million. Question E. Use logarithms to find the year in which the funds will first exceed $700,000 on the 30th of June. Okay. I'm going to assume that's talking about the original question, which was when we were using that P was equal to $10,000. Okay, so this was using the sum equals 135,000, 1.08 to the power of n minus 1. So it's resorting back to the equation that we found in part B. Okay, we want to have a sum of 700,000 or more, but I'm going to make it equal to 700,000. These kind of questions, you can make them into inequalities, but often it's easier just to solve them as an equal to sign, and you know you just have to round up. Okay, divide the 135,000 across to the other side, and you don't want to round, because that doesn't go nicely. You don't want to round down to too many, like your decimal places off too soon, because when you're doing logs of things, rounding is going to make a significant difference sometimes in what your answer comes out as. So I left it as a fraction. If you do 700,000 over 135,000, I put down 140 over 27. Okay, then you're going to have to add the 1 across to the other side, which gives you 1.08 to the power of n. 140 over 27 plus 1 is 167 over 27. Now for the sliding base. N equals log base 1.08 of 167 over 27. And then you type that in to your calculators that will do it all for you. What did you get?
23.6.
That's right. Therefore, the 24th year. Okay, question 3. Charmaine has a superannuation scheme with monthly instalments of $600. First thing to note is we're talking about months. That changes things. So $600, that is a monthly payment. But the 10 years, that's going to have to be 120 months. I'm going to have everything in months. Yes. No, you can't, unfortunately, because the rate of interest that you're getting is going to be monthly as well, because you're putting the money in more regularly. Good question, though. So it's always how often you put the money in is how often you have to compound your interest. Okay, so also this 7.8% per annum, that's wrong. So we need to turn that into monthly. So you go 7.8 divided by 12 and also divide it by 100 while you're there. So it's 0.0065. That's as a decimal. That's not a percentage anymore. For a month. Not a percentage. Important to note that, because I don't want you to divide it by 100 again. I already did that. Okay, so starting with our first installment. It was $600. My interest is 1.0065, adding the 1 onto the interest rate, to the power of 120, because it was 120 months. Our second one, we're just going to reduce that power down by 1. And that pattern would continue down to the 120th month. We would have $600, 1.0065 to the power of 1. Okay, the total amount, starting with the A120 would be 600 times 1.0065 plus next one will be 600 1.0065 to the power of 2 plus ... all the way up to 600 1.0065 to the power of 120. Aren't you glad you don't have to write out all 120 terms? The sum of the 120 terms will be the first term, bracket, the interest rate, which was the rate of the series, 1.0065 to the power of 120, minus 1 all over 1.0065 minus 1. Is everyone okay that I'm just subbing straight into the formula? Just the A bracket R to the N minus 1 over R minus 1. That's the sum formula. What did you get, Finlay?
109. So 109,206.94.
Very good. Oh, there is a part B. There's still more. Okay, so on to the next section. So that's our answer for part A. What'd I do? Yes. Yeah, that's it. No, it isn't one. Yeah. Okay, on to B. Charmaine was offered an alternative scheme with an interest of 7.8% per annum, compounded weekly with weekly installments. What weekly installments would have yielded the same final value as A? So we not only have to change our interest rate and our N into weeks, we have to use the sum of our last one to go backwards and find out what their investment each week would need to be to get the same thing. All right, so first of all, 7.8% per annum. There's 52 weeks in a year, so 7.8, we divide it by 52, and while we're at it, divide it by 100. So 0.000015, that's per week. It is, well, it doesn't say it on here again, but it's the same 10 years, right? How many weeks are in 10 years? 520 weeks. Okay, so let's build our series. In the first week, the person, Charmaine, will invest M, whatever M happens to be, that's what we've got to find out. They will get 1.0015 for their interest, and then that will be for 520 weeks. The A2, we'll just be subtracting 1 off that power to be 519. And then we get down to our A520, which would just be in there for 1 week. So power of 1. So you can see I reduce this down to as much as I can, but you should always show the first 2 and the last. And then when we do our total, again, I do the first 2 and the last, even though it switches what it's going to be. So I'm going to start with the M equals 1.0015 plus M 1.0015 squared plus all the way up to M 1.0015 to the power of 520. Okay, the sum of those 520 terms will be the first term, there's my first term, bracket R, which is 1.0015, to the power of N, which is 520, take away the 1, all over 1.0015 minus 1. Now, I'm trying to find the M, remember? So this is the point where I go, I need this sum to be equal to the amount that we would get if we were doing this monthly, like we were in Part A. So in Part A, we were told we got a sum of 109,256.94. And then we make that equal to, actually, can we tidy that a little bit? Oh, I'll do it later. I started writing it now. I'll put 0.0015 on the bottom. Okay, to get the M, you need to get rid of all these things. So the one on the bottom, it's going to time, you could divide that if you want to, that's fine. Or you could times that one over and divide the two brackets on the top underneath. So it would be 109,256.94. I'm going to times the 0.0015 and then divide the 1.0015 and the 1.0015 to the 520 minus 1. I could have simplified it different, but that's okay.
270.
Nope. That's way too big. I don't want to pay that every week, do you? 138. What did you do, Kieran? Because that was huge. Boy, $138 a week is a lot more doable. Yeah. So if they put in $138.65 a week, they would get the same amount of money as putting in $600 for a month. What's better? Yeah, it is. Because if you think about 600 a month, it's about 4 weeks. That's 100. That's equivalent to 150 a week. So because it is compounded more frequently, you get more money faster. So you can start with less to get the same amount. All right, we're not done. There's one more bit. Oh, I've got to talk about it here. Which scheme would have cost her more per year? So in Part A, Charmaine had $600 that she was putting in monthly. So if we times that by 12, she is paying $7,200 per year. Whereas in Part B, they were paying $138.65 times 52 weeks, $7,209.80 or 80 cents per year. So you can see there is a Part B. Oh, it is costing more. Oh, I was wrong. Look at that. It actually looks like Part B is costing them more. Did I times that right? It must be those extra few days that I wasn't counting in my weeks that makes all the difference. There you go. So therefore, the scheme in Part B would cost more. They're putting in an extra $9.80 over the year. Not by much.